Namaste and welcome everyone. Welcome to the session 7, the final session of the programming bootcamp. Previously in session 6, we covered a linear regression, and we are going to continue from there. Before we continue, are there any questions or comments? Okay, let me share my screen. Right, so session 6, we discussed linear regression, and I think I have copied this in my session 7 folder as well. So because we are going to continue the discussion of linear regression, so I copied it here too. So basically, there's a PDF, and it's from some lecture notes that prepared for my machine learning course. So this PDF is from there, and this is good in VS Code. You can open PDFs and looks quite okay. So basically, in session 6, or in section 5, we covered traveling salesman problem and simulated annealing, and essentially we looked at function optimization problems from using simulated annealing. And so simulated annealing is a way to optimize a function, and we discussed I mentioned that there's an example of a function is Rosenbrock function. So this is an example. And basically you can optimize this using simulated annealing, but in simulated annealing, you are doing a random walk, meaning you're adding random noise to your new as your new solutions, and you either accept or reject those new solutions. Over time, you go to global optimum, or somewhat near a global optimum. That means you found your solution. Whereas in gradient descent is another optimization strategy, and gradient descent is in the root of machine learning, deep learning. It's all built on gradient descent. And the thing is, when you have hundreds of thousands of millions of parameters or decision variables, as in deep neural networks, then you cannot do things like use stochastic algorithms like simulated annealing or do random walk. You need some better information to form new proposals or new neighborhoods in a solution, right? And that is when you need gradients. And basically, gradient descent is based on the idea of using gradients to actually explore a solution space. And this is another example of a solution space, or in the simulated annealing literature, it's called the energy space. And this is just an example of a function that is being optimized. And we saw code where we reviewed, we went over these using gradient descent, where the thing is that if this is the function, you need to find the gradient of that function. And in the previous class, we saw how we can compute the gradient, and then using the gradient, we iterate over time, and eventually we find a solution which is somewhat close to 9/4, right? So that's the gradient descent for you. So this example, this is just a function, and there's no data associated with the function. And in machine learning or basic or statistical learning techniques such as linear regression, logistic regression, and basic machine learning such as logistic regression, perceptron, and a neural network, you are dealing with data. So you could assume this as your model, which does not have data at the moment. But when we are looking at the basic of machine learning, basic of statistical learning, that a very, very basic is linear regression, right? And linear regression, the very basic cases where you are dealing with one variable, which is your uh, also in this case called an explanatory variable, or sometimes called predictors, and you have your response variables, right? So you have, and you have a data set with an input, that's your x, and that's your output, that's your y. And yeah, I had a COVID jab yesterday, so I'm a bit slightly dizzy, but I'll try my best. Um, so we plot these. So the green ones are what's plotted, and then we need to basically find a slope that fits the what has been plotted well. Okay, and what, and that is actually your linear regression model. What is your linear regression model? It is the slope essentially. And a slope, a straight line, basically is represented as y is equal to mx plus b, and x here is all this list of these values. Okay, so it can be any value in this line essentially, and m and b are things that you find using gradient descent, right? These are the two variables that you need to find using gradient descent. And in this case, it is the m is represented as w0 or weight 0, and sorry, the b is represented as weight 0, and that is also the y-intercept, right? And it is and your m is your weight 1. Okay, so basically this is just another way of writing it. The reason w's are used there because this slowly builds onto neural networks, and in neural networks there are hundreds or thousands of uh, these variables, and they are known as weights. Okay, so that's basically a neural network could be seen as a layered ensemble of linear regression models, something like this, right? So, and basically, we want to find this. And in order to find this, we need the good values for W0 and W1. We need a way to kind of see what those good values are. So we can plug in, we can guess these values here. You can also use a simulated annealing to find this, by the way, okay? As a programming exercise, you can do it. You can take the code of this linear regression, and in the place of gradient descent, you can place a simulated annealing and use simulated annealing. You will use the same, and this will become your energy function or cost function. So in this case, what is our energy function or cost function? It is just a sum of squared error function, okay? And it is half sum of squared error function. Why is there a half in front? It is because when we are going to, that's just a constant, right? And the reason that is done is because when we are going to calculate the gradient of this becomes easier. It becomes more simplified, right? So this whole function can be represented again with this, where you see mx plus b, you now know where that mx plus b comes from, right? Just don't be too confused about this, because I know that here on top here, it is mx plus b is assigned to y, but this is different, right? This is the yi here is what is your data, right? And mx plus b is your model. So basically, this is your model, and then the green points there, or boxes, that's your data. Okay, and basically you need to get the difference of them and keep on making square roots. So basically, like maybe the regular data is at different regular intervals, and then you are going to plug in that or you're going to read the data that's indexed by I, and n is the number of data points. Okay, so that's basically your error, and this is a very important part. And how that is implemented is just given here. For every point, and let's say your data is denoted by points, and your M and B is what you're trying to find, and basically every point has a X and a Y, right? Component. And basically that whole equation that you have on top there, you see the Y is what you got from the data, and X is also what you got from the data. Okay, so you got your Y and your X, and then the M and the B, the M and B are things that are being proposed, right? They are, in the beginning, you are going to just guess it. So you're going to just put random value for M and B, right? So you can put, let's say your M is 0.2, B is 0.5, something like that. If you put those two values, this sum squared error, it will give you a value, right? And that's basically your error. That's just the beginning, right? And then in iteration one, you are going to compute the value of M and B using gradient descent. And gradient descent means that first you are going to find what is the derivative with respect to M, what is the derivative with respect to B of that function, right? And the derivative with respect to M is this. It's essentially the same function. This goes in front, that's why it's 2 goes there, so 2 over n, okay? And then this disappears, the power disappears, the exponent disappears because it's 2 minus 1 is 1. And then basically in there, everything remains almost the same, okay? So everything remains almost the same. The thing is, you see the model there remains the same. The inside is same. So this is like a composite, treated as a composite function, and you find the derivative of that. So you find the partial derivative with respect to M, then you find the partial derivative with respect to B. Review of partial derivatives and derivation. There are a number of online tutorials. Please visit them if you are doing this programming bootcamp without that knowledge. And in this later, I will also give some links basically. So this is an example that we look at, and in here basically this is a series of points that's plotted, and we want this red line to basically fit in there. Okay, and you can run this there's an animation about what when the gradient descent algorithm is training this, and your value for M and B, they will keep on changing over the iterations, and that's what gradient descent is all about. Linear regression is all about, right? So in the neural networks literature, linear regression, when you put a step function to the output, so whatever you are predicting, basically in the above case, what we had was that we had only one X, meaning X was univariate or one-dimensional. In the case when X is multidimensional, then you are going to have something like this. And then basically the model is where you multiply x1 multiplied by w1 plus x2 multiplied by w2. So that's what's written here, plus x, it keeps on going, multiplied by wn. You keep on adding, and then you subtract this from the bias, minus w0. W0 is your B, okay? So bias. So that's till here, it's still a linear regression model. But the moment you put a step function to whatever you get, so you get a prediction there. So let's say prediction is 1.5. What a step function does, it checks that 1.5 If it is greater than 0, it says it's a 1. If it is less than 0, it's a -1. So a step function is basically discretizing your prediction. So if the prediction was, let's say, minus 0.5, then step function will say, it's a -1. Okay. So if you have a binary classification problem, for example, you want to predict if somebody, if this is a iris flower or not, something like that, or this is uh, um, this if there's an example about some classification problem, this is this person's face or not, if it is a face recognition, things like that, then you could use this model and and do classification. So this is an example of how a linear regression model can be extended to do classification. Okay, and your part 6, and basically from this is again showing the error surface, and your exercise 4 part 3, I think, is actually asking you to do this, actually, to extend your linear regression model so that you can see if it can be applied to a classification data set. Okay, so you can see that, and there are some tutorials on Maths is Fun and Khan Academy. I think this may open, well, it's a PDF. Hopefully the link is still working. If not, then just do a Google search of partial derivatives, Maths is Fun and Khan Academy and chain rule. So basically, uh, in that case, now we are dealing with basically a multivariate linear regression, right? That's what a perceptron is also known as a perceptron in the class in a neural networks literature. And in there, basically, we have to find these partial derivatives with respect to each of those values. So now, in the first case on top, you just had W0 and W1, but we have now lots of these W's because our model has lots of these things, right? So uh, and then basically we need to find the partial derivatives with respect to each of those weight values, and this is basically how it is. And more generalized notion is given here. Basically, then you find this, and which kind of comes to this using chain rule and the partial derivatives, and essentially your change in E over change in W, your this is basically your derivative, right? So basically it's simply the output minus your predicted, right, multiplied by the input, right? Your X is your input. Okay, so it's output minus predicted multiplied by minus of the input, and we are going to see, and that basically derivative is taken to compute your weight change, right? And that derivative, what you have there, is basically used to do your weight change. So what you have here in an algorithm, in a gradient descent embedded algorithm for perceptron or linear regression with a step function, which we want to use for classification. And this whole thing can be also used for regression, okay? So it will also work for multivariate regression problems. What is an example of a multivariate regression problem? We are going to look at some examples next, okay? So for example, a univariate regression problem would be like, let's say that you want your linear regression model to kind of predict what is the house price or house rent price in an area, and in your data set you have a list of locations, let's say all around Sydney, where the house price is given. A lot, I mean, you have like what, I mean, hundreds of cities, small towns in Sydney, right? So let's say all these towns and city suburbs, you have a data set of all the prices, and along with all the prices, so that price, you can think of it as a Y, which is a response variable in this case. so y, which is a response variable, and x in that case, in this example, would be, let's say, distance from opera house, right? So if you are in Blacktown, your house price is, let's say, the average rent for a week. House average rent for a week is, let's say, $500 in Blacktown, and the distance is from opera house could be, I don't know, maybe 30 kilometers, right? And if you are in Kensington, then it is $700 for a two-bedroom, and the distance is, let's say, 5 kilometers. So these are the x variables are is the distance from the opera house, and your y would be two-bedroom average price of the location, right? So that's, and let's say you have a lot of data plotted, and you just need to find a line that fits well. So that's an example of a univariate linear regression model. A multivariate linear regression model is when you have more than one x, right? So more than one x would be like, okay, so your x1, let's say x, the first x is x1 is the distance, right? The distance from opera house. But your x2, which is another feature, your x's are your features. Your x2, which is another feature, that would be the time from opera house to there. X3 could be, so the other feature is the time taken, average time taken to travel, right? X3 feature is a 0 or a 1. Does this location have a train station, for example? X4, another feature could be the age of the number of years, or the since when this building was constructed. So is it a new dwelling or a old one? And another feature could be, you know, estimated valuation price, something like that. So you have like series of features, and this series of features actually do decide the house rent or flat rent in a location. Okay, so that's a multivariate linear regression, and that you have all the series of x's, and these are all those examples I've just given. And that you are, once the model is trained, the model will be, you give all this series of x's, let's say a new location, and basically that model will basically give what is the house rent. So that model can be used by your landlord, your rental agent, right? Or rental agents would be having some kind of a similar strategy, which they may not be revealing, but they would be having some kind of a linear model, I think. Right, so that's a very basic example of a linear model in a multivariate case. And here we have another case with this data set and being trained, and over time we want the to reach the lower value. Basically, this is saying how the data set is how the linear regression model is training this. So one important part is how can linear regression model, the things that are predicted, how good are those? So one way to measure what is good is an error, and we have seen that the sum of squared error. But there are other ways to see the quality of your predictions, and that is, one of them is called an R score. And R score is something you calculate similar to an error, and basically if it is negative, it says that there is no relationship with your um, x variable to your y variable, the predictor in what is being predicted. But if it is exactly one, that means it's a positive linear relationship. So that's the equation of the R score. Uh, And basically, I think that equation is implemented here, which is very simple, right? This is basically implemented here using Numpy. Okay, so this is not that actually. This is Pearson correlation coefficient. That's what's implemented. It says here. I'll have to check this actually. Okay, so this example was not for R score, but this is for Pearson's correlation. And the R score is actually given here, the R squared score. And essentially, that is basically your Y minus the Y predicted and Y minus the mean of the Ys, right? That squared, 1 minus that. So that's your R squared score, right? So the R squared implementation would be somewhere in the code. And then we have, yeah, so that's the implementation there. And you can see the links for more details. And that's the implementation in the case of R. So, okay, that's all for linear regression. And I think we did go over linear regression just on Monday. So we'll just go over it again quickly. You have your main program, which is basically calling your gradient descent runner. And in your gradient descent runner, we are giving it the points. Basically, the points are actually given here. So that's your data. So this is your X and that's your Y, right? So you can assume, let's say X is, distance from Opera House and Y is the rent price. But in here, in this case, nothing is mentioned, but that's just an example. So that is being called in a for loop by the number of iterations, and as simulated annealing, we need to know maximum number of iterations. Gradient descent, we can use, I can define maximum number of iterations. So for how long you want to train this, and basically you get the gradients and you take those gradients, step gradient function, and then you basically the step gradient function computes the gradient, which is there, and then it computes the value for B and the M, right? The B and the M, and that B and M you take, right? You take and you compute the error, and the compute error function we've already seen. So that's basically how this works. Just a moment. Let's quickly compile this. Okay, I'll give you a few minutes for all of you to actually run this in your own computer. You can pull the kit and let's see, you run it, can it run? Okay. Okay. It's called linear stretch. When you run this, what you will see is your iteration number, and then you have all these things that are being printed, and where is it printed. I think in the last class I gave a print statement. It's saying it's running, so it's calling this is being called there, and these things are being printed here. What you see there, let's say I, B, M, and error. Okay, so these things. So you see in the beginning, the error was very large, and over time, that error kind of from 1,000 in almost 10 iterations, it converges to 112. And the values that you started with, your value for B and M, they were there. And here you can see these are the two values basically. And it keeps on going, but these values do not really change that much. So it's around 0.3 and 1.7. But in the error also doesn't change much. So that means it has converged to a solution when your proposals, these are kind of your proposals or your weights do not change. Okay, let's please uh, place in your chat if you have were successfully anybody successfully able to run this. Please mention in your chat. Okay, great. Thanks, Hakim. Any questions, Hakim? No. Okay. So we go into the next one, which is linear regression, but we are using not the code from scratch, but in this one we are using the code which is taken from some example. And in this case, we've seen this example in our previous session, the iris dataset. Basically, there are three types of iris flowers. So it's a multi-class classification problem, specifically three classes. And there are four features in this dataset. So that's a iris dataset. And you can see that in this there's a function there called get data in this code. Okay, so in this function, in this code, basically we want to kind of use what is already out there, a machine learning library called scikit-learn, sklearn. Okay, and that's basically given by this sklearn import datasets, import linear models. You can import your mean squared error, R2 score, and then all these things that I was telling you previously, they are already implemented for you. So a lot of machine learning and data science is people just using what's already implemented there. Whereas the goal of this bootcamp was not about using what's already there. It's about knowing how they have been implemented so that in the future you can have a good new idea, you can implement something from scratch. Why is implementing something from scratch important? Because it depends what sort of machine learning or data science jobs you do in the future. Or if you do a master's or a PhD, what your projects involves. Like if you want to do a master's or a PhD where you want to contribute to key data science or machine learning journals, it's not about taking what is already implemented by others and applying to some problems, but it's about improving what's implemented by others. So that is why programming is very important. So, okay, so that's the background. But here you can see there's a load Boston data set. So this is like, which I have commented. So there's all these UCI machine learning data sets, which I showed you earlier session, the UCI University of California Irvine website. And you can follow these links to see some of them. Basically, they are preloaded in the sklearn library. Okay, they are all preloaded in the sklearn library, and essentially you can use them. But here I just wanted to show, what if there's data set which is on your computer which you downloaded, can you load it? Yes, this is how you're loading it. So we are loading it, the iris data set in this example, but we are never actually using the iris data set because you see it's data set there, right? But that is here we are it's loaded, and this variable is data set, whereas this is data sets. Okay, so this is data sets. Why is that data sets? Because we are saying import data sets, right? So that means that we are accessing the sklearn library using data sets. So using the data sets, we are saying load diabetes, and there's load iris, there's load Boston. So that's the Boston house price data set. So there are many data sets there. So with just this, you will just have the entire data set, right? And then you can split it into a training and a test set, right? This way, or you could, this is saying that only the last 20 points, 20 instances is the test set. And so the X train is all your features, the training, and X test is all your features, the test set. That means the last 20 of them. And your Y train is all the decision values. That means your classification. So in the diabetes data set, it's a binary classification data set, I believe. And basically in there, we need to classify if somebody has a diabetes or not, something like that. We can check that, and there's data sets in the UCI machine learning repository. Okay, so it says diabetes data set. Okay, so that's the diabetes data set, and it has. I'm not sure. I don't think this is the exact diabetes data set that we are looking at. There are sometimes a different, like there are data sets probably of different types of diabetes. Yeah, the one that we are looking at is the FEMA Indian diabetes data set. Okay, so there's the data set. So we just say FEMA. I think. So that's the FEMA Indian diabetes. So it's in Kaggle, and it's also in the UCR machine learning repository, right? And basically, this is the data set that we are looking at. So, and it has 9 columns, and all these features are there. They are the features. And the outcome is either 0 or 1. And that's what we're trying to, in a classification problem, we try to classify if it's a 0 or a 1, something like that. So that's what's being done. That's what the FEMA Indian diabetes data set is. Go back to our workspace. And we can also generate synthetic data. And in here, we are generating some synthetic data. And in this example, basically, it is also implementing a linear model by Numpy, right? So here we are implementing a linear regression model by Numpy, using Numpy. So you can see the gradient function is kind of using dot products, right? So what we've discussed earlier, the linear regression from scratch, that's implemented again so that it can take care of not univariate cases, but multivariate cases where you have more than one feature. So that's what this is actually doing. And it's calculating the new set of weights. So now we just don't have one weight value, we have like a list of weight values, okay? And that list, the size of that list depends on the number of features in your data. So in the linear, so it's number of features in the data. So in the case of the diabetes data set, you have 9 features, so you'll have 9 weight values plus 1, which is the extra one is the bias. In the bias, the weight 0 is the bias, so total is 10 weight values. Okay, so that's a example. And then we have other examples of this linear model, and we have linear model dot linear regression. Let's see where this linear model comes from. So it is actually coming from sklen. Actually, it's not scipy, it's sklen. Okay, so let's and then basically in this one, when you're using sklen, because everything is pre-built, you just call your linear model and say dot linear regression, and then you say you assign it somewhere, and then dot fit, you give it the training data, and you give the training features. That's x train, and y train is the outcomes, okay, of the training data set. And then you check, yeah, then you basically with this your model will be trained. That means your weights and biases are trained by your gradient descent. But in here, this is just one line of code. The implementation is done in the scikit-learn library, and we don't see the code. Okay, we only see this interface. With this, basically, you're using the code. So all that code that we are just showing here on top, it could be something similar, but we don't see that code in this version. And essentially, we then get the predicted values by giving it the x text, right? And whatever is the y predicted, we can then calculate the mean squared error by y test, which is that what is in the data versus what is being predicted. And that's your mean squared error. And then you can also calculate R2 score. And both of these mean squared error and R2 score are already built-in features of the scikit-learn library, right? And so that's, we do a get data, we then do a scikit linear model, sklen, sorry, sklen or scikit-learn linear model. And let's run this quickly. And we did for that problem, and then we did for another problem. So in the first one, we used the sklen library, and then we generated synthetic data, and then we used the Numpy linear model. Okay. So it's showing things. The first one, so the first thing it shows is a data set. It says get data. It says iris data somewhere. Where did we use iris data? Let's see. So it says iris data. So we just printed this data set, but we are not actually using it. This was just, I wanted to show you. So let's just ignore both of them. We don't need to read them. So let's run this again. Right. So what do we see? The first thing, it says those are the coefficients. There's some coefficients it's printing out. And then it printed out a mean squared error. It printed out a variance score. And that is done using the scikit-learn linear model, actually, for the diabetes data set. So that's being done there. And then we generated a synthetic data, and then we are using a linear model, Numpy linear model. And basically the Numpy linear model is for the synthetic data, that is it is calling these functions and printing things there. It says converged. And what is these things that are being printed? What are these things that are being printed using the Numpy version? Because it says converged there. That means now you're not making much. Your new weight minus the weight is less than the tolerance. That means your set of weights are not being changed too much now. So it's better you just stop. Okay. See, we did not tell it the maximum number of iterations. This will keep on running if this was not there. And then basically we are printing the iterations and the mean squared error. Okay. And you see the iterations are there, and in the beginning the mean squared error was somewhere around 7, and then it reduces and keeps on reducing to around 1. Okay, and then it doesn't improve anymore, and you can see that the mean squared error is almost not changing much. That's why it converges. So that's all for the linear regression, and this is the previous one, I believe, where in this one the data is plotted, and the output of the model is plotted as well, and that's where the plotting is done is here actually, the scatter plot, where the x test and the y test is being plotted, right? So, and that's what you got, and that's basically your linear model there. So basically that ends the linear regression and multivariate linear regression here. Just opening the floor for questions or comments, and let you run this for another, give you another 1 or 2 minutes to run this and see it for yourself. Okay. Then we'll move into the next topic, which is logistic regression. Okay, so logistic regression, basically the model looks almost the same as the linear model, the first part, but the only difference is that the output, the activation function, in the previous one, you don't have any activation functions in the linear model, but in the Perceptron version, you have a step function when you are going to use it for classification problems. But in here, there is the activation function that you use is called a sigmoid activation function or a logistic function. So in the statistics literature, it's called a logistic function. In the neural networks machine learning literature, it's called sigmoid. It's basically the same thing. Okay. So what means is that, let's say whatever was your z, if your z value was -2, then the function will give something around 0. So it's basically -2. It's somewhere around 0.2, let's say. If your the z value was 0, then it would give 0.5. And if your z value was, let's say, 4, then it's something around 0.9. That's the output of the sigmoid. So what the sigmoid does is basically squashes your outputs between 0 and 1. Okay. So then the reason it's used mostly for classification. So what is a logistic regression model is basically using the same linear regression model and just putting a sigmoid activation function at the end, so that you can use it for classification problems. In classification problems, you could say that if your output is greater than 0.5, because of classification problems, it will squash your outputs between 0 and 1, and if it is greater than 0.5, you can take it as a 1, less than 0.5, you can take it as a 0 in some cases. So, and that's the equation, and that's basically the Numpy implementation. So here's an example of a dinosaur meme. This is the age of memes, right? So we see this dinosaur and this little girl. If it's going to, I mean, just historically, this never happened, but in the cartoon world, anything can happen, right? So in the cartoon world, this little girl is riding this dinosaur, and the dinosaur says that would be $15 Sigmoid, and then says thanks for the ride, Dino. Here is $15 Sigmoid. So $15 Sigmoid means $0.99999. Okay. So why? Because in here, assume this is extrapolated, and so it will be very close to 1. Okay. Number 15. So that's basically a linear regression, and you can use linear regression for exogate problem. Exogate problem is that your feature 1 is A, feature 2 is B, and your output is, and you just have 4 features in an exogate. If your A is 0, 0, then your output is 0. If your A is 1, 1, your output is 0. So typically this was used to train a linear regression model and neural networks in the past. So linear regression is also called perceptron, and logistic regression is also called perceptron. And the only different, there are 2 types of perceptrons, basically one where you have a step function and one you have a sigmoid function. And if you have a sigmoid, then you would need to find the derivative of a sigmoid, and the derivative of a sigmoid is basically derivative of this is that. So if your sigmoid was given by S, then it's Sx multiplied by 1 minus Sx. So this part is what we are going to, so the thing is, when you're using gradient descent, note that with gradient descent, you need to derive your squared error function, right? And your squared error function is using your model. And your model in the case of linear regression is a simple linear model, but in the case of logistic regression, your model takes that linear regression model and then does place a sigmoid over it. So to derive it is going to be a little bit different because the derivative of the sigmoid is a bit different, but eventually it's just using this in your equation. So we'll go over another example here. Let's see that we have this example where we have this GMAT score, GPA, work experience, and this data set is kind of admitting people in a university, I think, or not admitting. So 1 is admitted, 0 is not admitted. Or it could be university postgraduate, or I think this is not a university postgraduate thing. It is because you're looking at work experience and GPA. It could be GMAT. So it could be, yeah, could be PhD or maybe some job at Google or Yahoo or Facebook, something like that. You know, that's why they're looking at work experience in GPA. So, and the GMAT scores. So basically that data set, you could save it in a file and load, or you could just place it like this. That's the same thing. And basically we need to implement this thing there. Let's just implement it. So sorry, go back there. And basically that's this data set is being loaded there, and then you calculate, you do this is the code for making the prediction, and there's a code for for getting the coefficients, and basically this I am implementing it here again using a nice class which is called Logistic Regression, and this is done in object-oriented programming, and all of you by now may be knowing object-oriented programming, and that's how the sigmoid is done, and this is actually a log loss. So loss functions, there can be several types of loss functions, and in this case we have a log loss function uh, which basically is similar to squared error loss. It does the same thing, but if you are using a log loss, your gradients change a little bit as well. But the general idea is same, where you basically have the iteration, and for that number of iterations, you find what are your predictions, and then you calculate the gradients, and then you keep on doing it till the maximum iterations are reached, right? So basically that's that there, and we are using that on a iris data set. So we are using this on an iris data set, and basically here this means that the X train, we are using only feature 2 of the iris data set, and looking at the targets, and we in this case basically we were just classifying the iris as a, because the iris data set is a multi-class data set, which is there are 3 classes, but our logistic regression code at the moment can handle only 2 classes. So what we did is basically we treated class 1 as 1 and class 2 and 3 as class 2, something like that, and that's what it does here. And then for that many iterations, we train that model using a logistic regression model. And basically that is logistic regression. And the same thing is done with the previous code data. And we have a linear regression, the scikit-learn version, and logistic regression, scikit-learn version. And just very similar to linear regression, we have this. We can tell what is the solver, and based on whatever solver, it can be used to make this calculate an error. And in here, basically, that error is calculated using Numpy, but you could always, and also in here Numpy, but you could always call the scikit-learn function that calculates that error, which is not being done in this case. It was done in the previous cases. But that's how actually linear and logistic regression is implemented using scikit-learn. Just to note that in here, in this case, because the things that you pass into your logistic regression, if it is multiple classes, then you would have to say multinomial. That basically means that there are more than 2 classes. Okay, if you don't say it, then by default it treats it as binary classification. And in here, this is a type of optimization algorithm. It's also a gradient based optimization algorithm, and there is, you know, several different types of gradient descent implementation. And in here, if you use gradient descent, you can just say SGD, or stochastic gradient descent. That kind of ends our notes on the linear regression. We'll take a 2 minutes break, and then we will move into the area of neural networks, and we'll go with very basic neural networks examples and code, and so on. So, and if there's some questions or comments, please put it in the chat. Yes. Thanks, Hakim. Tarun, most of the files are actually Python files are given here because I am taking these notes from my course resources. I cannot give all that information, so some of the links will not work. Sorry about that, but I think more than enough is here. And like when you're doing the exercises, then you can use these, or you could also look for content online. I mean, it's a 2 hour. It's just a 2 hour class now, which we are covering linear regression, logistic regression, and basics of neural networks. Typically, this is done in a few weeks' time. So this is just a condensed to give you an overview. It's like your subconscious mind knows about it. You don't have to know too much of the details. You just have the overview. And then over time, you use this overview to go into the details. Okay, I'll let you run that code that was there and things like that, and we'll continue in 2 minutes. Okay. Okay, so let's continue with the next part, which is introduction to neural networks, right? So what is a neural network? I mean, you've been hearing this all along, but it's hard to escape this term because it comes on the news a bit too often, especially if you're following things. Okay, I will check Tarun then week in week one folder. Okay, I'll get back to you, Tarun, about this. So yes, so what is a neural network, right? So basically, it's hard to not know this term if you're following news from Google research, from Facebook research, and Tesla. They are all saying we are using neural networks, deep learning to do a number of things, and basically, uh, what are those things? They are doing using it for recommender systems, for autonomous driving systems, for fake news, spam detection, and these are some of the very common things that you hear that neural networks are being used for. They are quite successful. And basically, neural networks are based on the perceptron, and we have discussed, seen what a perceptron looks like. This is an example of a perceptron. Basically, it's based on a linear regression, multivariate linear regression model with a step function, or it could be this, could also be a sigmoid. And so in the case when it's a step function, we can use an XOR gate, and basically that can help you decide, and you can change your the weights using gradient descent, and you need to make a decision boundary as shown here. And this is done using perceptron learning rule. The perceptron learning algorithm is very simple, so it's a while not convergence. And convergence is, you could set it as a maximum number of iterations, or when you reach your error is not changing, or the weights are not changing, something like that. So you could have 2 or 3 different ways to implement convergence. Then you pick a random input, so you pick a random value from your data, right? You pick a random data point, and then basically from your training data points, and then basically you update your weight, and this is based on the based when in the case when you have a step function. When you have a step function, you treat it, the training, as you are treating, you assume that it's similar to a linear regression model. Okay, so that's a very basic step algorithm there for that. And we have some code there, which you can see the link later, which shows basic perceptron. So and I'm not focusing much on the perceptrons because we have already seen linear regression and logistic regression, which are equivalent to perceptrons. Okay, so now let's move on to neural networks. And neural networks, the term is basically there when it's motivated from biological neural systems, where you have neurons, as in our brain or brain of other animals or reptiles, and they have neurons, and they are interconnected with links, and those links are called synapses as well. And basically uh, you have input, some sort of input to the neurons, and then there's some sort of operation going in here, which is weighted sum of incoming inputs, which you can implement using a dot product, for example. And then basically you have some outputs. So this is an example of how this kind of relates to a perceptron, right? Planning, where you have, in this case, you have not one but multiple outputs. And this is your inputs. You could think that these are connected to your eyes. Then you have millions of neurons with trillions of interconnections. So the brain has billions of neurons with trillions of interconnections, the human brain. And that's why they say the brain is so complex. It's even in that complexity, it is still being debated if consciousness is a product of the brain, and how is the mind an emergent, how the mind and the brain are related. And there is this mind body problem in philosophy. Read up about mind body problem, it's interesting. So but nevertheless, just these things, I mean, that's going into another area, but basically the area of artificial neural networks are motivated by that. And you have a sum of incoming neurons, and then you have some bias, and then you have some outputs, and then you use some activation function. And that's basically what a neural network is. And it can be used for applications such as assisting a driver or autonomous driving system. Note that this system was Alvin, and Alvin was developed in 1989. So that's about quite a while ago, 32 years, something like that. And even now, we don't have this implemented fully. It's still in a test phase, and sometimes it's working, sometimes it's not. But the one that's implemented by Google and Tesla, it's not just one input camera. There are a number of cameras and sensors, and there's a very very comprehensive decision-making process. Okay, so you can see this, and you can see a perceptron that uses a sigmoid activation function. So this is a perceptron with a sigmoid activation function, and this is basically multivariate linear regression, logistic regression, you could say. Note that in the case when you, in the statistics field, if you have, do not have a binary classification, if you have multi-class classification problem, that's not called a logistic regression, but that's called a multinomial regression. Okay, that's called a multinomial regression. But in neural networks, you use feed-forward neural networks either for binary, you will say I'm using a simple neural network, or feed-forward neural network for binary, or multi-class problem for prediction, for regression. It's all just called a simple feed-forward neural network, or a multi-layer perceptron, or a feed-forward neural network, or a backpropagation neural network. Okay, a backpropagation neural network, backpropagation algorithm. And what is the backpropagation algorithm? It's basically a way to train a neural network. And this is what a very simple neural network looks like. You have input features, you have hidden neurons, and you have output neurons. Basically, you calculate each of these hidden neurons. You can think of them as either linear or logistic regression model, right? So you have like inputs connected to it. Then here you have all these inputs connected to it. Here you have all these inputs connected. So you can think of it as linear, let's just say logistic regression models just stacked next to each other. Then on top of it, there's another two logistic regression models. And basically these, so it's a neural network is a hierarchical logistic regression model. We could think of it as an ensemble of logistic regression model, a stacked ensemble of logistic regression models, and so on. Okay, so that's basically a neural network. And what we need to do is in neural network, there are two major operations. One is forward propagation, where we compute using the input features. We compute the output in the hidden neurons and the output in the output neurons. So that's called forward propagation. And back propagation is when these outputs that are computed, they are compared with the actual data, right? In the training data, the responses in the training data or outcomes in the training data. And they are basically then you use gradient descent to propagate error or gradients back and do weight updates for different layers. So these are all the weights. So this is typically you would say this is the weight from the input to the hidden and weight from the hidden to the output. Note that now the architecture is more complex when you compare to a logistic or linear regression model, and hence these weights we cannot represent using a array, so we have to use a matrix. So this is matrix 1, matrix 2. What are the outputs of the hidden layer? That can be an array or a vector, array or a vector, right? And the input can be also stored in an array or a vector. So that's what is happening there. This is this forward propagation. Your output, that's Z, that's taking your weights, taking your bias, and multiplying it by the input, and then adding it to the bias, and the whole thing is your Z, basically. So this Z is what is here and here. So this is layered. So basically the operation repeats. So you could develop it as a layered operation. And basically the thing is that this is a very simple feed-forward neural network, but you could have 2 hidden layers, 3 or 4 hidden layers, and there are more complex neural networks such as deep neural networks. They have more than those, convolutional neural networks, recurrent neural networks. So you do not want to have separate weight matrices declared in your program for all these. So sometimes you can have 3-dimensional matrix that basically represents them, but we will not do that right now. So we have the feed-forward neural network. We will look at that later. So we have this feed-forward neural network code, how the forward propagation is done, or it's also called the forward pass. Okay, so this basically takes your X, which is your input, and it just does a dot product on the X minus the bias. And that's your Z1, which is your output. Z1, you can think of output there. And then you can put that output into a sigmoid and get final output, which is done there. Z1 is placed into a sigmoid, and then you have self dot here and out. For example, we have then we have the next, the Z2, which is the output layer, and you do a dot product, and you can read up about the dot product and how it's implemented in Python. And what the dot product basically does is basically it does to calculate this. It does whatever is there, input multiplied by the weight. Let's say this is weight 1, weight 2, and weight 3. So input 1 multiplied by weight 1 plus input 2 multiplied by weight 2 plus input 3 multiplied by weight 3. That comes as Z1, and minus the bias. So each of these neurons has also a bias weight. You can imagine that. So minus the bias, and that's your Z1. And similarly, after all these Z1s are calculated, then you calculate the sigmoid, make the sigmoid function, get the sigmoid value of that. Then you treat that as input to calculate the what is the z's in the output. Okay, so that's what's being done here. So that's a very simple implementation. Looks niche, but if it's difficult to understand, then we also have a for loop implementation of that. Basically, that whole the dot product, you can use this for loop, and basically the for loop, nested for loop can be used to implement whatever is the hidden output. So this is same as that. The operation is almost the same. It's exactly the same in terms of the answer that you'll get, but it's just that it's implementing using a for loop. The other thing is a loss function is squared error loss. And basically you take the whatever is the output, the final output multiplied by actual output. So y minus y dash, something like that. You subtract that, and then whatever that error is, you find the square of that and you divide it by the number of outputs. So that's called the squared error loss. And basically you have a forward propagation, then you have white loss, then you have a back propagation. So that's the overview of your gradient descent based back propagation. So the back propagation algorithm has two major parts, which is forward propagation and back propagation. So the backward pass, the back propagation, these are the equations of the back propagation. And basically the gradients are computed and those gradients are propagated backwards, and then you have a white update. That is implemented in code using Numpy. So you have the first, you calculate the gradient of the output layer, and then you calculate the gradient. So this version was just, I was just trying to show how that can be done using for loops here, but that same thing, the back propagation, rather than using for loops, you can just use dot products, and basically you get something like this. So the forward pass was on top and the backward pass is this one. And basically both of them combined because it becomes the back propagation algorithm. So the back propagation, the output in K, the gradient is basically output multiplied by 1 minus output, and then the actual minus output. So that is basically implemented here. Desired my output, that's the multiplied by output multiplied by 1 minus output. So that's basically implemented there. And this part for hidden is that you need to take whatever the gradient was there that's computed, that gradient you will multiply it by the weight, the existing weight, and that is multiplied by the output, and you do this operation using a dot product, right? And so that's what's being done here. So that's the output delta, which was done here, that is multiplied by the hidden output. The hidden output basically means the hidden output, what is there. So basically the gradient that is calculated here, that is a dot product of that is done in relation to this. So it's basically, in a way, uh, we need to kind of compute what is the white update for each of these links. Okay, so we need to compute what is the weight update, and to compute that weight update we need the gradient for the output layer, and we need the whatever is the hidden outputs, right? Why? Because that's how what gradient descent uses. The gradient descent to weight, to even in a logistic regression or a linear regression, when you're using gradient descent to the weight update, you do the W multiplied by the X. The X in this case is this, right? And moving on, we have that part is kind of done here. So that's the gradient multiplied by the weight, and then it's also then multiplied by 1 minus output multiplied by the output. So this part is then gives the gradient of, so you are, what happens is first you computed the gradients of the output layer, and then you need to compute the gradient of the hidden layer. Okay, so that's what, to compute the gradient of the hidden layer, we are taking into account these weights and the what is the output of the hidden layer. I know in the first time it's a bit looks a bit complicated and messy. Don't be worried too much about the exact minor details. Just know the overview, and then over time, when you implement this, when you look at the code from scratch, then it will slowly start to make sense. So we have found the gradients of the output layer. We found the gradient of the hidden layer. Now we need to use those gradients to do a weight update, right? So that is weight update is done here and here, which essentially means that we take the gradients. So now we have computed the gradients of the output and the hidden layer, and now we need to do the weight update in this backward pass. And so W2 is actually your weights from the hidden to the output layer. W1 is weights from the input to the hidden layer, right? So you take whatever is the gradient from the output delta, you multiply it by that, and that basically gives, multiplied by that, which is the output of the hidden layer, multiplied by the gradient, multiplied by the learning rate, and learning rate is like a alpha, or a learning rate is what is given by the user, right? And that basically computes the gradient for the output for the weight 2, and the bias 2, which is the bias of the output layer, that is basically computed by -1. So you see this part here is same as the previous one. So but this is multiplied by the, so whatever is the gradient, that means in the only difference between the bias update and the weight update is that this was multiplied by the output of the hidden layer, whereas in here the output of the hidden layer is not multiplied. We take that as a -1, because the bias is connected to a input which is -1. So that's the difference between the bias weight and the actual weight. And the same is actually done here, where the hidden layer delta is used to calculate the update the weights of the input to the hidden. So that's the basic general overview. The details you will slowly learn after reading all these, after looking at how the gradients are computed. You need to learn a bit more about all these things, but the purpose of this was just to give you an overview. And this is another example of a neural network, and this is also what we would call an autoencoder. Autoencoder is where your inputs and outputs are the same. That means the goal of the neural network is to try to learn the inputs. So your input is same as the output. Okay, so autoencoders are typically used to compress data. So this was your data, and if the neural network can predict that same data with only 3 hidden neurons, that means that many 8 hidden neurons are compressed as 3. And you can take the prediction of the 3 hidden neurons, and that's basically your data being compressed. Right? That's what autoencoders are doing. So after it is trained, these are your hidden values, let's say. So, and they give these outputs. So this is These values basically can be discretized, like this 0.89 will round off to 1, this will round off to 0, this will round off to 0. You can say that if it is less than 0.5, it's a 0, and greater than 0.5, it's a 1. Then basically with 3 bits, you are representing this information. So the learning, it takes 2,500 epochs for this to be trained. And these are just visualizations of how the error is. The sum of square error of all the different outputs are reduced over time. And this is the weights from input to hidden unit, and that's taken from the machine learning book, how they are changing over time. So the derivation of the error gradient, we see a similar example as the previous one. Basically, the derivation is done uh, in a similar way, where you have the output with a squared error loss, and where the only it's a similar way where, when compared to the perceptron learning, but note that we have sigmoid output neurons, right? So if you have sigmoid output neurons, you need to take that into account, how the sigmoid is derived, and eventually basically you will get this as your um, gradient, right? And this actually is a gradient that you got here. That's actually in what we implemented in the beginning when we were looking at so that what's implemented sigmoid derived is what we get. That's the output. It's the output desired minus output multiplied by output minus 1 minus output. So that is what you get from the derivation actually here. That's what you get from the derivation there. So that's all that we have. And then the thing to note is that that's the sigmoid function, but in case if you use, there are other activation functions. You can use a linear activation function, you can use a 10-H activation function, and ReLU, Soft Plus, Softmax, and others, and they are all used for different types of neural networks. And in neural networks, depends on the activation function, the gradients will change. So computation for the gradient changes. So in my code, I am assuming that the activation function is a sigmoid, but if your activation function is linear, then your gradient will change. And if your activation is 10H, then it will also change. So typically for multi-class classification problems, one hot encoding is used in the neural network machine learning literature. What that means is that if your color is red, green, and yellow, that's your output or outcomes. And let's say that there are 3 outcomes, then that can be represented by 3 output neurons. Basically, red would be this, both red basically means that the first one is a 1 and that the rest of them are zeros. Yellow is this, and green is that, right? So that's basically a one hot encoding. Moving on, then we have other things. Data processing, you can process all this data using one hot encoding, and we have covered data processing in the previous classes. And then now we go into number of hidden layers. Basically, that is, people think that just adding hidden layers will solve the problem. Not really. It depends on the size of your data, and you need to, usually 2 hidden layers at most are okay. Most problems can be represented with 1 hidden layer. Sometimes, like, you need to calculate, estimate how many weight links are there. So, and it depends on your neural network and your data. You need to do trial experiments to determine the number of hidden neurons in the hidden layer and the number of hidden layers. At most, two hidden new layers would be okay for most problems. Okay, so moving on, we can see so neural network code from scratch. We have version 1, and you have a class, and you have Sigmoid activation function error forward pass, and that's the first one. Version 1 is using for loops, okay, and backward pass also all computing the different. So the first, these ones are the till code till here. It's calculating the gradient of the output layer, the gradient of the hidden layer, and then that's just doing the weight updates. Then you need to, after your trained neural network is trained, you need to test your neural network. So that's basically the code to test the neural network. And this is where the magic happens. That's your back propagation using gradient descent, where your forward pass is for each. So it's very similar in terms of when you compare it with linear and logistic regression. Basically, you keep on doing it till you reach the maximum epochs or some kind of a minimum performance in terms of error, or it could be classification performance. And then you basically you look at your data set, you can pick data randomly, pick points in the data set randomly, and that's what stochastic gradient descent is doing. Or you can just pick it from the beginning. This is just for demonstrating to the end. And here you have a forward pass and the backward pass, and you keep on updating. We keep calculate the error, and we also have some kind of a mean squared error. And as we are going, we are also storing or saving the best set of weights and biases. So looking at the data, then we take the two different, there are a number of data sets, iris, 4-bit parity, and exogate. Exogate 4-bit parity is an example. It's an extended version, you can say, of exogate. You can read about it. It's basically you just look at the number of ones in your input, and if you have even number of ones, then it's a 1. If you have odd number of ones, it's a 0. So that's the data set. So you have like a 4-bit parity. If you have, this is just your data set, and there's no test data set. The training and test data is the same, but it's not such an easy problem compared to that. So it takes more training time and neurons in the hidden layer to learn this. So this is when you have even number of ones or zeros, ones. So you have 4 ones, that's a 1, and you have 3 ones, that's a 0. 3 ones, it's a 0. So that's an odd number. 2 ones, it's a 1. 3 ones is a 0, and so on. So, and then you have exogate problem, and which is there. But in this exogate problem node, I'm just putting some outputs. I just placed this ones there, but let me just put it to stop confusing. Let's just assume that we have mirrored outputs, meaning that so that we can learn this exogate problem with two output neurons, right? So this is like now a one hot encoding version. Okay, it's like a one hot encoded. When it's one hot encoded, you will have two output neurons in a binary classification problem, right? Three classes, three output neurons. So number of classes is number of output neurons. That's one hot encoding. So this is one hot encoding. So let's run this. So it's running. Essentially, over time, the error is going to reduce, and that's what's happening. And it's trained. It does. Let's go into the version 1 again. We are calling the neural network class, and we are doing a multiple number of experiments. So in this case, we just do 2 experiments. You can do 10 or 15. And for every experiment, we report the classification performance, and we get the mean and standard deviation of that using the FNN.3. So that's what we get that output. So that's the FNN from Scratch version 1. The FNN from Scratch version 2 is basically the same thing, except it's a more neater, smaller code where we're just using the dot products and Numpy operations. We're not using the nested for loops. Otherwise, everything else is exactly the same. Okay. So that's the FNN, and you can try the different problems. And over time, you can see the error, squared error loss is reducing. That means the problem is learned. So that's the FNN from Scratch. And let's say that you want to develop a FNN where you have multiple number of hidden neurons. Note that in here, we have this weights, weight 1, bias 1, weight 2, bias 2. But that is because we assume that we only have one hidden layer. If you have multiple hidden layers, and the number of neurons in each layer, basically we declare it in the main, and basically we define a topology. So we say input, hidden, output. Okay, and the input is basically what we give depending on the number of features in the data. The hidden is something we specify for different problems. Looking at the number of features in the data and the size of the data, we ran trial experiments and we said, okay, that many hidden, like for example, exogate, we are okay with 3 hidden or 2 hidden. And with iris, we are using 6 hidden, and 5 will do, 7 will do, 8 will do. You don't have to use too many hidden neurons there, like 20 or 100 hidden neurons, because the data set size is quite small. It's only 150, and the number of features is only 4. Okay, so whereas and the number of output depends on how many what classes you have. But if you put another hidden here, this will basically not work, because the neural network cannot, the code is not built so that it can work with more hidden neurons. In order to actually have more than one hidden neurons, the reason I'm doing this is because I wanted to explain to you how classes can be used. Then you for doing something like that, how object-oriented programming can be used for doing something like that. Obviously, I'm a bit tired because of the already jabbed yesterday, I guess. So I'll quickly show this and basically end the session. That's the neural networks from scratch. And I was supposed to have a neural networks. Yeah, not a very nice way to name these things, I guess. So there's a neural networks from advanced. That's another folder. And there's a data and there's a neural network. Let's look at the data. So those are the data sets and there's a neural network file. So in the neural network advanced, we have a layer, class layers, okay? And in each layer, basically, we have weights and biases, outputs, and gradients, right? And then we have a neural network class, which is using the layer class. Then basically all the things, the train, test, all these things are placed there. But in the neural networks class, we define that say that, okay, and maximum we will have like 20 layers or something. So we define a memory structure. And then we fill these layers with a different number of weights, the size of weights is defined by our structure. So in this basically, and then we can print what your neural network looks like. We have the activation function, individual errors, forward pass, back propagation. And in this version, I'm just showing up till forward pass. And then we are reading these different sets of data sets from the data folder. And we can use scikit-learn to transform these data sets into, like, say, in the typically neural networks, you need to transform the data sets between 0 and 1 in the input for the input layer. If you do not transform, it will still work, but it creates a bit of bias, so some problems may not, the neural network may not do as well as supposed to. So it's good to transform your data set, especially if you are using linear activation functions. If you are using sigmoid activation functions, it may not change that, make that much of a difference. But to transform data, you can always test what your neural network performs with and without transforming data to see. And basically this function is, this is a much neater code, meaning that it it works quite well when you looking at the number of hidden, when you look at the number of hidden layers, right? So at the moment, what we are doing is we're defining a topology. We're defining a topology, and let's just run it. And it is input features, whatever the input features are. We don't have to manually tell that. You know, it gets the input features from the data. Output features, it also reads and gets from the data, right? It just reads the data automatically. You tell it the data, ensure that the data is in the right format. It will get the input and the output features from the data. Then basically, what we need to do is develop your neural network topology. Of course, the first will be the input features, the last will be the number of outputs. But the hidden is something we need to specify. So for example, here I said hidden of 5, okay? So, and now we say Python neural network. So, and this, note that this code is taken from my GitHub here, and the whole code is there, FNN multiple layers. So you can pull that later and run it if you really want to see it's working or training. At the moment, it is one train. I just wanted to demonstrate how your neural network topology is done. So this is the topology is done. So that's the input to the hidden weights, the hidden to the output weights. Just because here we are doing print network. Okay, printed network. It just takes from the layer 1 and it goes to the end and it prints. In layer 0, we also have a weights. So in here, this is just to initialize the input features. So input features are stored in the layer 0, And that is we are using over time to initialize the rest of the layers. If you can see the forward pass here, the forward pass, in the forward pass, we do not have a Z1 and a Z2, we just have a Z because it's somehow using this for loop and initialized that layer 0, the input features, and it's taking it in a recursively using a for loop, it updates the hidden layers. Okay. So in the case if we have, and the back propagation is basically using the forward pass. And you will have a similar backward pass, which is given in the code link on the top. I knew that I couldn't cover it, so I didn't really place it again. So let's say that we want to have 3 hidden neurons. Let's say same. Okay, in one of them we do so 3 hidden neurons, but in the middle, it's a bit less the number of neurons. Let's just run this. So now it did run, and that's just done for one pass. Okay. So now we have that's the data. This is just the data being printed. Okay. So this is the data, that's the input iris classification problem, and that input is kind of transformed between 0 and 1. Okay. So that's why you see those values. And I'm just doing this for a small data in the iris case of the iris classification, just to show you that this is working. And then these are the 3 classes using one hot encoding. Okay, the one hot encoding is there. And basically you have hidden weight 1. Then you have the weight. This is weight layer 1. Then you have the weight layer 2. Okay, just the weight layer 3. Then you have the weight layer 4. Right? Can you see this? We see the weight layer 3 because that was and that they all depend on the size of your hidden. Okay, so have a look at this and try to make sense of it. Basically, that's the way where we are using object-oriented programming. We are using better programming techniques to develop this neural network, and that's how it's working. So you can see the full code here. And then there are all these exercises that are also given for the different parts or and part 1, 2, 3 we discussed. So part 3 is more of a linear regression where we look at the iris classification, and we also try to experiment with the step function in the case of linear regression, which we talked about. Then part 4 is logistic regression, and you can do all these things using these different data sets. You may have to read a bit more if you, because I did not really cover IUC and ROC curves, precision repulse score, and all these things. You can Google about them and read them. There are different ways of measuring error. And part 5 is just the neural networks, and you can do a number of things. It's just a basic FNN from scratch or scikit-learn version. And you can see how other optimizers are being implemented. And in this neural networks from scratch, the code that I'm discussing, I'm trying to implement the ADAM optimizer, but that's still in the review. We're still testing it. And you can add other things such as dropouts. You can read about them and other things. So the thing is this exercise 4, if you really do these parts, it really makes you ready for a machine learning research in the future, or become a data scientist and things like that. It's not something that can be done in a day or two. Your exercise 4 can take a few weeks to be done. Okay, so I let you look at all these, and it was a pleasure teaching and being part of this, and I'd like to thank all these people who are attending today. I will send a survey and get some feedback about this. So please say something on the chat if you want to say something. Uh, Still being recorded at the moment. Else we'll, yeah. Anybody wants to say anything? Any comments on the chat, or you can use the mic about the bootcamp, how it went. So, okay. So thanks, Tarun and Abhimanyu. And thank you, Hillary, Thomas. Thanks for very kind comments, and thanks for bearing with me. Some days I was a bit dizzy, of course, yesterday with this COVID jab, and last week I was a little bit sick. So my apologies with all that. But please keep these videos. They will, I mean, make use of these videos and make use of this code and use it in your PhD, in your masters, and in developing courses in the future. If you become a lecturer, if you're going into secondary school teaching, uh, feel free to always drop an email and so on. Right. So what I will do next is send a survey to everybody, and basically all these people, all the people who have somewhat completed some of the exercises, there will be an online certificate basically of completion. It won't be like a certificate, but it will be more of just placing your name, affiliation, or address or something on in the programming bootcamp repository to show that you completed the program. That's your name, and that I will ask you if you want to do that. So I'll send a survey by the weekend, and if you have seen several videos, gone through some of these things, if you want your name there, then you can indicate so. Anyways, it was a pleasure. I'll just stop recording now. Okay, stop recording.